Thank you for having me give this seminar. What I've tried to do for today's talk is the following. If I can get the slide to advance, yes. So I want to try to tell you a little bit about what active matter is, why should we care about it, and things like that. And then I will try to walk through a pedagogical story, life in a day in the life of a theorist kind of thing. Where I try to tell you a pedagogical story about hydrodynamics of active pneumatics. Then I'll transition to a show and tell segment where there won't be enough information for you to actually understand everything that I'm saying, but there'll be cute movies and advertisements for recent things that we have done. And then finally, I'll transition to coming attraction sections where I'll show you movies of things I don't understand at all and that we are trying to understand right now, and then make some brief concluding remarks. So let's get started. What is active matter? The field got started by physicists looking at movies such as those that I have on the screen. And physicists being physicists, they did not look at these movies and think, oh, what beautiful natural phenomena. They thought, hey, there are a bunch of particles here that have local interactions and have long-range structure in them. I know what this is, because as physicists, we know that we can have local interactions and get long-range structure. The prototypical example is icing models, where nearest neighbors talk to each other and you can get global ordering in the system. So they said, oh, these guys must be flying spins. Let's just make spins fly around off lattice, and there are local annealing interactions between those spins, and that should give me flux. That was the first paper that got this field started by Vichek and co-authors. But subsequently, this field has evolved to describe various systems like those in these movies that I have here. The leftmost movie over here is cytoplasmic streaming in the oocyte of a Xenopus egg. It's a big egg cell. And when it's ready to make a baby, so to speak, it can set up system-sized flows in the system. Another example that I like a lot is crawling motility of cells. This is a movie of a white blood cell, a neutrophil chasing E. coli. This is bacterial swarming, where the colors are drawn on the movie to show which are the flocks that are moving together. And this guy is the cartoon example of a flocking system, which is just nails on a plate. It's a vibrated plate with some short particles on top of it. And the vibration of the plate is what is activating the system, and it can give rise to these kinds of flocking patterns. Now, all of these can be unified within one theoretical paradigm by saying the following. Each of these are materials that are made out of microscopic engines. So instead of having microscopic ingredients that are obeying Newton's equations, I have microscopic ingredients that are obeying second law of thermodynamics. They're consuming energy and doing work. And these local engines are coupled to each other in various ways. And this coupling leads to them interacting in such a way that they are able to do work at much longer length scales. That's the theoretical paradigm that unifies these diverse systems that I have on the screen. Now, just to understand why this is a different class of systems for us to consider, let's think about a theorist's favorite non-equilibrium material, which is a sheared fluid. When I shear a fluid, what I'm doing is I'm putting in momentum on the scale of the system. So on a very large length scale, I am putting in momentum into the system. That's what I mean when I say I'm shearing the system. And what happens is the collisions among the molecules of the fluid randomize this momentum into temperature. And so the momentum that I put in at the macroscopic scale becomes temperature at the microscopic scale. So the energy cascades down in scales. I'm putting in energy at the longest length scale, and it cascades down to the lower length scales in my material. And thermodynamics gives me a handle on how to think about this. I know how to think about entropy production, and I know how to think about regression and reciprocity and stuff like that. It gives me some handle on how to think about driving in this context. But the problems that we're considering here are upside down, in the sense that I'm driving the system at the micro scale. Everything I know about the laws of thermodynamics happens at the level of the single entity. There's energy consumption and some work is being done. And that work cascades up in scales and results in some collective dynamics at a much longer length scale. So this inverse cascade problem we don't know anything about. So what the rules of the game are and what are the design principles that one can use to design or harness this cascade is something that we don't know, and we've been trying to figure out for about 15 years now. Okay, that's all cool, but why should I care about it? So for a moment, if I wear my theoretical physicist hat, then I think these systems are interesting because they are liberated from the constraints of equilibrium. When the system is at equilibrium and then I drive it away from equilibrium, I let it go, it comes back to thermodynamic equilibrium. There are a lot of constraints onto what the system can or cannot do. And those constraints are the things that manifest themselves as fluctuation dissipation relationships, regression analysis, reciprocity, and things like that. None of those constraints are true anymore. So you have an unconstrained and uncharted landscape of phenomena that you can explore. And you get all kinds of new physics that would be disallowed at equilibrium, the most famous of which is the long-range order in 2D, which is prohibited by the Mermin-Wagner theorem, but also anomalous fluctuations, instabilities, pattern formation, things like that. We'll see a few of these example phenomena as we go along. Okay, that's a theoretical physicist hat. But as a taxpayer, why am I spending your money to do this research? Why should you care about it? The wearing a real person's hat, the answer that suggests itself is to say that this paradigm of a material is the physical scaffold of biological systems. You and I are just materials because we are just atoms and molecules arranged in particular configurations. But what makes us different and what makes us living in some sense is associated with this energy flow through my system from the micro scale to the macro scale. So studying these kinds of systems provides an understanding of the physical scaffold of many biological systems. And what one hopes to be able to do by studying these systems is one hopes that one can design materials that have biology-like properties, adaptive, self-healing, and things like that. And perhaps one can identify interventions to unpleasant things that biology does. This is an approach that active matter people working in tissue morphogenesis and cancer and things like that take this biomechanical or mechanobiological approach to understanding stuff going wrong in biology and see if you can design interventions once you understand the physics at play. But for our purposes, and given that it is a MateriAlZ seminar, let me try to underline this point, which is, what do I mean by design materials, adaptive, self-healing, and stuff like that? And I want to underline this point in the context of a particular example. Let me go back to my crawling cell. This, in my view, is a smart bag. It's a bag that can move and navigate and achieve function. This movie that I'm showing here was made in the 1950s by David Roberts at Vanderbilt. Obviously, subsequently, this movie has been made many times. And here is a more recent movie from the lab in Genelia Farms, where it's the same cell that I'm watching under a microscope. But now in purple, I see the actin filaments, and in green, I see myosin motors. Myosin motors are the fourth generation entities, and the actin filament is the polymeric scaffold. It's the material backbone of my system. And what you can see is that I have high myosin motor activity at the rear end of the cell, and I have a lower myosin motor activity at the front end of the cell. And if I just took the stresses that are there in this material and ask what this system is doing, I can see that there is a large local contraction, contractile stresses generated at the back of the cell. There are extensional stresses generated at the front end of the cell, and it's this combination that results in the global displacement of this bag. So from this cartoon picture, I can set myself a materials physics objective as follows. What this thing is it's the same microscopic ingredients, it's the same actin polymer gel and the same myosin motors, but spatiotemporally organized in order to get dynamic and adaptive reorganization of what's happening. And that's what is resulting in function. In this case, the function is motility. So what I want to be able to do is I want to be able to make materials that are spatiotemporally programmable in terms of what internal stresses they have. I want a material that has high stress in some regions and low stress in other regions, or programmable rheological responses and things like that. That would be like a materials physics-y goal of trying to understand these kinds of systems. Okay, now that is my big picture introduction of what active matter is and why you should care about it and stuff like that. If all of that is okay, I'm transition to the second part of my talk, which is the pedagogical theorist story that I want to tell you about an active material. And the story that I want to tell you is to imagine that my active material is made of a collection of interacting units that are producing forces. I don't want to know about the details. I don't want to know microtubules, motor proteins, actin, myosin, and all of that other stuff. I don't want to know any of this. I want to think about it along the lines of I would think about water when I'm trying to figure out what is the pressure gradient I should set up in order to pump water through a pipe. I don't need to know anything about hydrogen bonding or the polar nature of water as a solvent or something else like that to figure out the pressure gradient, right? I just need to write down Navier-Stokes equation. That is the attitude I want to take to the active materials in this segment of the talk. And if I wanted to take that attitude, what I need to do is I need to be able to classify my active materials based on symmetry. Now, the first symmetry that I have to consider is the symmetry of activity. What do I mean by that? I have some object that is generating forces. The forces are typically a force distribution on some object, right? And if I have a force distribution, exactly like one does when one is taking an E&M course or something, you take multiples. You make a multiple expansion of that distribution and see what it looks like. If the leading order term is a dipole, namely that there is an arrow along one direction is the leading order description of the force generated by that entity, I would call that symmetric activity. That would be the example of birds and bees and stuff like that, which are all moving in one direction. Then another example would be there is no net force exerted by the system, but the leading order contribution to the multipole expansion is a dipole. That is to say there are two forces equal and opposite exerted in two directions. That would be the kind of distribution that dipolar or nematic symmetry of the activity, and so on. I can have higher order classifications. Then the second symmetry that I have to consider before I can write down the hydrodynamic description is the symmetry of interactions. What do I mean by that? I mean that if supposing two particles come together and the result of their interaction does not change the active force at all. They keep exerting forces in whatever direction they were exerting in before they started interacting with each other. Then that would be an example of an isotropic symmetric interaction where the interactions do not reorient the active stress in any way. That is one category. Then another category would be if two guys come together, they end up becoming parallel to each other. This would be birds and bees and things like that. If two guys run into each other, they're going to become parallel to each other. They won't keep pushing in the direction in which they are running in. So that kind of reorientation properties of the interaction describe the symmetry of the interaction. Then I want to take these two ingredients and use that to develop a hydrodynamic or continuum description for my active material. Just to say that this kind of symmetry classification is useful, I want to give a few examples of active materials that people have built, sorted by my symmetry classification. So if I want to imagine polar drive, namely that these guys are self-propelled moving along some arrow on their body axis, and isotropic interactions that when they interact, their active force is not reoriented in any way. The example that belongs in that category are these Janus colloidal systems. These are PMMA or similar colloidal particles with a metal cap on one side. And these guys are immersed in a hydrogen peroxide solution, and there is a hydrogen peroxide to water chemical reaction catalyzed where the metal is. And the resulting Marangoni flows result in propelling this colloid in some direction. And they interact through excluded volume interactions. They are spheres. Excluded volume interactions don't exert any torques. So I get an isotropic interaction. Then another example in the category of polar drive and polar interactions would be something like this over here, which is a motility assay, where you take, for example, a glass cover slip or a lipid bilayer or something like that, and you put a bunch of motor proteins down on it. And then you put some filaments that interact with that motor protein on top of it. The motor proteins will propel the filament along their long axis. That results in self-propelled rod-like particles. They'll have polar interactions when they collide with each other. And that kind of system belongs in the polar drive polar interaction category and leads to phenomena such as these propagating waves and things like that. And some bacterial systems also belong in this category. And for the nematic drive, nematic interactions category, this is the system that I want to spend a lot of my time talking about. There are in vitro systems made of cytoskeletal filaments and motor proteins. I'll tell you about in a minute, but that the description that I'm going to talk to you about applies to tissues and cell sheets and various other things like that. So it's been used quite widely. So what I will spend the next 10 minutes or so is talking about the theory of this third class of active systems. And the description that I'm going to spend a lot of time building the theory and so on applies to a lot of systems. I will tell you about this system, the cytoskeletal stuff, in a minute, because that's my bread and butter. But the monolayer of vibrated granular rods, bacteria swimming around in liquid crystal suspension, cells on substrates, bacteria under certain circumstances when they are confined to more or less 2D, are all systems that fall within the theoretical paradigm that I'm going to try to walk you through. The particular experimental system that I spend most of my time looking at data for is the system composed of these objects that I'm going to describe to you in a minute. There are these microtubules. These are specific polymers that exist in your cells, but for the purposes of our conversation, they are just rods. Then there is a bundling agent. Again, this is a PRC1. It's a particular microtubule associated protein. But for our purposes, if two rods come together, they induce an attractive interaction among the rods so that they spend time close to each other. That's all we care about. And then there are these motor proteins. These motor proteins are the stress generating entities in my system. They consume ATP and walk on these polymers. And what happens is that this bundle is extended along these two red arrows here. So it does this, it's pushed out this way. And you put a whole bunch of these down and then centrifuge them onto an air-water interface, oil-water interface, and at high densities. And then you see, watch what happens under a microscope. What happens is this. This is a 10-year-old movie now. And this ice cream churning dynamics that you're seeing here is the theoretical description that I'm going to walk you through slowly. Okay, now theory. You have to bear with me for about 4 slides. There will be lots of equations, but then we'll again transition to movies and storytelling. The amount of information I want to put into my theory is just that my system is made out of some rod-like particles that are exerting force dipoles. There are these 2 double-headed arrows of forces exerted by these particles, and they live in some dissipative medium, say a viscous fluid. And the only other piece of information I want to add is that they are rod-like particles. So when they come close to each other, they tend to align. That's it. These are the 2 pieces of information I want to have in my theoretical description. Then this suggests that my theoretical description should consist of 3 variables. The density of particles. I am dealing with the rod-like particles in a cup. The density is a conserved quantity. So that's one dynamical variable. Then there is a nematic order parameter. This is a tensor order parameter, but basically what it does is it measures the local orientation of my double-headed arrows. If my double-headed arrows are all pointing in random directions, then this order parameter would be 0. If all my double-headed arrows are lined up, then this order parameter would be 1. And the tensorial character is just associated with the fact that it's double-headed, so I have to make sure that up and down are equivalent to each other and things like that. Then finally, I have the fluid velocity. Because momentum is a conserved quantity, I need to worry about the dynamics of the fluid velocity. My system is isothermal. I'm not going to care about temperature and other fancy things like that. So this is the description I want to talk about. But for the purposes of the conversation today, I'm going to ignore the density. I'm going to pretend that this is not relevant and everybody is homogeneous at all times. For the story, I'm going to tell you. Maybe if I have time at the very end, I can tell you a little bit about what happens when you relax this approximation. Okay, now let's write down the theory. I want to start with an equilibrium nematic fluid. So I imagine that I have a nematic fluid at equilibrium. That is, I'm imagining the LCD display in your computer screen or something else like that, some liquid crystal at equilibrium. Then you write down the dynamics of that system by saying that I can construct a free energy, F, that whose minimum is the equilibrium state of the system. And the dynamics of the system is just gradient descent in that landscape. This would be the conventional way one would write down dynamics for an equilibrium nematic liquid crystal. So I do that. Then I ask, supposing I impose some inhomogeneous flow on this liquid crystal, passive liquid crystal, what will it do? That is to say, I have these passive particles, rod-like, that tend to align and form a nematic. And then I want to impose a flow on that system that is inhomogeneous in some way and ask, how does it respond? And the way that you can understand how it responds is to think for a moment about a rod in some inhomogeneous flow. If there is some rod in some inhomogeneous flow, 2 things will happen. It will get convected with the flow, but will also be rotated by the flow if there are gradients in the flow along the length of the rod, right? So that is captured by equations of this form, which says that the center of mass is convected with the flow velocity, and gradients in the flow velocity can generate torques that reorient the rod. This U hat is the orientation of this rod. These equations that I've written down here are called Jeffrey's equations and were written down by Jeffrey in 1913 or something like that. So we've had more than 100 years of playing around with this equation, and everybody understands this stuff well. But given that I know what one rod does when I impose an inhomogeneous flow on it, I can take this information and ask, how will this order parameter be changed when I impose an inhomogeneous flow? And you can write down the resulting equation quite straightforwardly. It says that the order parameter will be convected by the flow, it will be rotated by the flow, and there will be a shear alignment, which says that the rods, even if they don't talk to each other, will tend to align in the extensional direction of the flow. So this would be the equation that I would write down for a passive liquid crystal when I impose an external inhomogeneous flow. Okay. Now, what remains to be done right now to complete building my theory is I need to write an equation for the flow. So let's do that. The starting point would be Navier-Stokes. The simplest equation that I can imagine for my fluid would be Navier-Stokes. These systems are incompressible, so it's incompressible Navier-Stokes. And I have to add to Navier-Stokes a bunch of things. The first thing I have to add is the fact that there are rods sitting in this fluid. If there is a rod sitting in my fluid, then there is some stress exerted by the rod on the fluid, just by virtue of the fact that where the rod is, there can be no fluid molecules. That thing is called the reactive stress. So you need to add to the Navier-Stokes equation the reactive stress that comes because of the liquid crystal agents that are present in my liquid. And there's a straightforward procedure to write down the reactive stress. That is to ensure that my dynamics is dissipative. By requiring that my dynamics be dissipative, one can identify the reactive stress. And this is something that people have done. It's called the Leslie-Erickson hydrodynamic theory and so on. But for the purposes of today's conversation, let's not worry about it. It's not important to the story I'm going to tell you. So let's not worry about this. And so my fluid equations are just going to be Navier-Stokes. I'm going to not worry about the reactive stresses that the liquid crystal part gives you. But I want to care about the active stress. These particles are not just rods sitting in a fluid. They are exerting forces. Each rod has this force dipole sitting on it. So given that each rod has this force dipole sitting on it, by just thinking about it for a moment, you will realize that the force density in any given region will be proportional to the nematic order parameter. It will be proportional to how aligned these dipoles are. So the stress, the active stress exerted by these particles on the fluid will be proportional to the nematic order parameter of the system. And you just add this piece to the Navier-Stokes equation. I have the normal Navier-Stokes and I add this piece of the active stress into my equation. And then I do one last thing, which is to say I drop all of the inertia terms. These systems are low Reynolds number. The experimental data that I showed you and the ones that I will show you, the Reynolds number to the best estimate is about 10 to the minus 4 to 10 to the minus 5. So I'm going to worry about the inertia and take it to be in the Stokes limit. Okay, that brings me to the end of my equation. So I have a theory. This is my theory of these rod-like force dipoles sitting in a viscous environment. Now, this theory has been studied for about 10 years now, and a lot of things are understood. What I want to try to do in the next couple of slides is use a bunch of cartoons and give you a feeling for the kind of physics one understands by studying this theory. And I want to begin by considering a perfectly aligned nematic. That is to say, all these rod-like particles are lined up in straight lines. And each of these lines here is many, many rod-like particles lined up in a straight line. And because each of them are exerting force dipoles, you can convince yourself that where they are aligned in straight lines, the guy below is exerting a force up, the guy above is exerting a force down, all the forces cancel with each other, and the net force along the straight line is zero except at the edge. That's what these arrows indicate. That if I had a monodomain, namely a perfectly aligned region of the nematic, then it will exert equal and opposite forces on the rest of the universe at the edge of the domain. Okay? Supposing that's okay. Now let's imagine that these domains bend a little bit. So again, I'm not bending any one rod. I'm imagining that the orientation of the rods move a little bit so that they are not aligned in a perfect straight line, but are bent a little bit. Then I ask, what is the net force exerted by this bent domain on the rest of the universe? Then by doing a little trigonometry, you will be able to convince yourself that there is a net force denoted by this red arrow exerted by these guys on the rest of the universe. And therefore, the rest of the universe will react. Newton's third law is one definite truth in the universe, if not anything else. So there'll be an equal and opposite force exerted by the rest of the universe on me. All of this stuff will start moving because of the reaction force from the rest of the universe. So basically what's happening is that these guys are pushing off of the rest of the universe and moving, right? And again, you should be able to convince yourself relatively easily that not only will they move, they'll buckle. Because you're pushing against the wall and you can bend, you'll bend more. So these things will buckle. So these lines will buckle and buckle and buckle until such time as they cannot buckle anymore. At some point, you'll have to, the buckling will be such that you'll have to bend any one rod. So at that point, you won't buckle anymore. And what you end up getting under those circumstances are these things that are called topological defects. These are regions where behind this region, all the rods are lying down. In front of this region, all the rods are lying up. There is one point in between where the orientation of the rod is not defined. That's what a topological defect is. A defect of this form is called a plus half. A defect of this form is called a minus half. And what the consequence of having these active stresses in the system is this formation of this plus minus topological defect pairs. Okay. Now, continuing along with cartoons to try to tell you the story of what is happening in this system. Imagine that I have a plus minus defect pair in my nematic order. I just take this configuration of Q, put it on the left-hand side of my right-hand side of my Stokes equation, solve the Stokes equation and figure out what is the flow induced in my system because of this orientation of my rod-like particles. Then what I will find is a flow like this. What's plotted here is the vorticity field of the flow. This pale blue region is a clockwise vortex. This pink region is an anti-clockwise vortex. What I'd like you to see in this picture is that when there is a plus minus defect pair in my system, I will get a pair of counter-rotating vortices for each plus half defect and 6 counter-rotating vortices around a minus half defect. Let's ignore the minus half defect for a moment and look at the plus half defect. What this is saying is that the flow of the plus half defect will be in this direction given by my blue arrow. So my plus half defect is effectively performing a breaststroke. It's pushing the fluid around it. And if the fluid is pushed along this white arrow, all of these straight lines will get bent. And if these straight lines get bent, again, by the same logic of the instability that I explained before, I'll get more defect pairs. So if I have a straight domain, it will bend. If it bends, it will form defect pairs. If it forms a defect pair, that will induce the formation of other defect pairs. This is basically the dynamics of a 2D active nematic. I want us to rewatch this movie again. This is the system with the microtubules. This is the different active nematic built out of different proteins and different ingredients. But you should be able to see with your eye the dynamics that I just described in my cartoons. There's a plus half, there's a minus half. The plus half moves along its long axis. And I mean, it's obvious to me. I don't know if it is obvious to you, but here there's a plus half that's going around. Here there's a minus half that's just sitting around. That's precisely the dynamics that your eyes are picking out when you're watching this ice cream churning movie. Okay. Now, this has been studied a lot. What you end up getting at the end of the day is a chaotic steady state with many plus half, minus half defects. It has been characterized in cell sheets, in swimming spermatozoa systems, and in the cytoskeletal systems that I was describing and so on. A lot is known about the statistical properties of the chaotic steady state that this system goes into. But for the purposes of today's conversation, I don't want to tell you about the chaotic properties. This basically concludes my pedagogical presentation. I presented to you about 10 years of work and understanding of everybody in the field by telling you a pedagogical story as to how to think about the math of the system and how to think about the physics that emerges in this particular system. Now I want to transition and tell you about some recent work that we have done in this system. And I want you to notice that the pedagogical story I told you only holds in 2D. All my cartoons were 2D and all my flow fields were 2D and stuff like that. I want to ask what changes when I go to 3D? The first obvious thing is that even if you bend in a plane, the flow you induce will not be in that plane. It will automatically induce flows out of plane. So the vorticity won't be in the plane anymore, right? So what are the consequences of that? Basically, what happens is that for a nematic system, there are 3 principal distortions that can be allowed in the system. They are called bend, splay, and twist. This is bend, this is splay, this is twist. I spent my time talking about the bend distortion and the consequence of the bend distortion to forming the plus minus defects and so on. I ignored the splay. Splay is the slightly good looking sister, a less good looking sister in the zoo, and nobody cares about it in the extensile liquid crystals. But it turns out in 3D, this guy is the star. Twist is the star. The truly three-dimensional deformation becomes a very important guy and plays a critical role. So I want to give you a couple of examples of things that we have done where we've seen the effect of this twist. Now, remember the story I just told you. There is a bend instability. If I have a uniform aligned active nematic, it will, if it is unstable to bend. The moment it bends, it will get distorted. And it might have been apparent to you in the way that I'm telling you the story that this is a long wavelength instability. The distortion will happen on system scale. But if you do this experiment in a confined channel, so you flow this material into a channel with some height h and some width w, and watch the uniform state become unstable, it does something like this. And what your eyes will be able to pick out here is that there is a characteristic length scale. The distortion is not system size. There is a long characteristic length scale over which the distortion is growing. And one can ask, where does this length scale come from? And this length scale comes from the twist in the third direction. The twist in the third direction together with the no slip boundary conditions basically give a fastest growing length scale. And you can do slightly fancy linear stability analysis on the theory that I just described in 3D and get the length scale, the fastest growing length scale, as a function of the confinement, as a function of the width and the height of the channel in which you're looking at the system. And then you can compare it to the experimental data and it is bang on. It predicts what happens in the experiment really well. So it's a validation of the fact that this idea that the twist is important and so on is reasonably borne out in the experimental systems. And this work was reported in this paper. Okay, now second example. Now, instead of this strongly confined 2D, 3D system, let me take a bulk 3D system and let's take a dense nematic in 3D. It's a nematic everywhere and it's dense. And I started initially aligned and asked what happens. Now, this plus minus defect story that I told you has to be modified somehow in 3D. And I want to ask how it is modified. And I want to first show you this movie over here. I'm just looking at the time to see, okay, I'm doing okay. I'll show you the movie over here. What you're seeing is a numerical solution of the hydrodynamic equations I described. And for just visualization purposes, you're only seeing the midplane of my simulation box. It's periodic boundary conditions everywhere and so on. And what I will be visualizing in 3D will be isosurfaces of low order. Remember, the amount of order in the system at the core of the defect is 0. Right? The defects are low order regions in my system. So I want to visualize isosurfaces of low order. That's what you're watching in this movie. And what happens is this when it goes unstable. Okay. Now, where is this? Let me pause it here. No, that's not where I wanted it to pause. I wanted it to pause here. Sorry, my ability to control my mouse is limited. Yeah, let's pause it here. Now, what is it doing? I'm unhappy with my. Okay, that worked. What I want you to notice is the low order regions are line-like. They are not point-like, right? In 3D, the objects that the system forms are line-like objects, not point objects. They're not point defects, but they are line disclinations. This liquid crystal people know pretty well because they have been thinking about this in liquid crystals for a while. But I want to go back to the beginning and watch the onset of the instability a little bit. And pause it here. This turns out to be the fundamental object that comes out of the instability. And this object is a neutral disclination loop. It's a wedge twist neutral disclination loop. And I want to spend a minute to try to tell you what this object is. So this object has a plus half defect at this point and a minus half defect at that point. So it has a plus half defect at one end and a minus half defect at the other end. But as I go around the loop, as I go around this guy, which is what is happening here, the director twists out of plane. So if as another visualization, if I start on a on a plus half defect and watch what happens to the director as I go along the loop, you can see that it twists out of plane. It twists out of plane and it twists a plus half defect into a minus half defect. That is the structure of this loop. And this neutral destination wedge twist loop turns out to be the fundamental object that emerges from a flat pneumatic in 3D active pneumatics. And this stuff, together with some experiments that produce this phenomenology, is reported in this paper over here. Okay. Okay. Now, again, continuing with my show and tell, we've looked at this. It turns out that the simple-minded story that I told you is not the full story. It doesn't always undergo a bend instability along the lines I described. And here is an experiment with the confocal visualization of what is happening. Under some circumstances, the experiment does what you think it will do, namely that it undergoes a bend instability in the plane, and it looks like the systems that we have already studied. But under other circumstances, changing what you put in the cup makes it buckle out of plane. As you can see in the confocal image, it's buckling out of plane. It's buckling like a film instead of buckling like a fluid. And it turns out that there's some elasticity that can appear in this system, and you can't think of it as a viscous fluid. You have to think of it as an elastic sheet and understand this instability. And what we did was we wrote down a theory which tells me when the system will buckle in plane and when the system will buckle out of plane, as a function of activity and elasticity. Then you go do a bunch of experiments where you change the ATP concentration, which is the amount of energy available for the motors to move, and change the bundling agent, which will be the amount of cross-linking that is present in the system, and find out when it buckles out of plane and when it buckles in plane. Then put these two pieces of information together and identify the material parameters of my system, the activity, the shear modulus, and stuff like that, as a function of the microscopic ingredients. So this is saying that I'm telling you how much, whatever molecule you put inside the cup, how is that related to the macroscopic material property of that system? And that is a recent thing where I'm hoping that this is a first step to actually quantitatively characterizing these materials, having my pretty hydrodynamic story tied to the real world things of concentrations of various things you put in the cup when you're doing the experiment. So this is, it's not yet published. We are in second round of fighting with referees. I hope that it will be out soon. Okay, now I'm almost at the end of my talk. So I want to go back to the material physics objective that I posed, which is that I want to make this bag and I want the spatio-temporally programmable internal stress and stuff like that. And none of the things I told you so far doesn't sound like that's where I'm getting, but I am getting there. And just to kind of make that point, I want to show some things that the experimentalists have done that the theorists have not yet caught up with. We're still trying to understand how develop the right language to understand this phenomenology. The experimentalists did the following. So I have this active stress, right? I have this stress that is exerted because these motors are consuming ATP and pushing on my filaments and stuff like that. Basically, force balance says that this is balanced by my reaction stress, whatever my material is doing to push back on me. And what they did was they changed the reaction stress by putting my stress generating unit in a polymer suspension. So they put it embedded in a polymer suspension so that the response is viscoelastic from my material. Then what happens in that case in the experiments is the following. At low polymer concentrations, I get back a behavior that the theory I presented actually captures very well. At intermediate polymer concentrations, I get this microphase separation, contractile stresses coexisting with extensile stresses and things like that. And at very high polymer concentrations, I end up getting global contraction. The whole thing just contracts as if it is a film folding on itself. So you can change the stress organization in the system by changing the concentration of your polymer that is there in the background at the same activity. So this gives me hope that I will be able to design different stress organizations in different regions in my material, right? And the theory that will help us understand what's happening here is ongoing. There are a bunch of people trying to understand this, and we at Brandeis are also building models and doing simulations and so on. I hope that we will have something good to tell you soon. Then another thing that the experimentalists have done to have local control over the stresses in the material is by making these light activated motor proteins. So they made motor proteins that are engineered to have this love domain. The love domain is a domain in the protein that allows a flower to open when it sees the sun and stuff like that, right? And you engineer it and put it inside the motor in such a way that the motor only becomes a motor and exerts forces when light is on. And in the absence of light, it just hangs around in solution. It doesn't do anything. If you make such a motor, then what you can do is you can use light to either have just rods hanging around in the fluid or turn the light on, and then the motors become active and the rods start exerting stresses. So what this allows you to do is experiments such as this, where you can see that the light is actually on only inside my yellow circle. You can see the rest of the fluid is quite static, and the stuff inside is moving around a little bit. And so what we have started to do in the recent past is build theories where we can do the equivalent of local light shining by putting active stresses only in certain regions of my space and ask what is the consequence to the hydrodynamics of the system. And the long-term goal of this thing, and we're writing the first papers on this topic right now, I don't have a clean story to tell you, but I will soon, is build optimal control. So we want to write down an optimal control framework where you will be able to tell me what dynamics you want the system to have, and I will be able to tell you what light pattern you should be using to activate the system so as to get the pattern that you want. And we've taken the first steps towards this by doing it for some particularly simple cases, basically so I can learn what optimal control theory is and stuff like that. And we're building towards actually doing it for the experiments and so on. Okay, and of course, then there's the bag. All of this stuff needs to be put inside the bag, and you need to understand what the bag will do. This is an example of some recent work where we put a microscopic model of active pneumatics inside a bag, and what it does depends on how much stuff is inside the bag and what is the flexibility of the bag and so on. And you get a zoo of phenomenology, which is reported in this paper over here. Okay. That basically brings me to the end of the spiel that I wanted to give you. Of course, I didn't do any of this work. Students, former and current, postdocs, former and current, did all of the work. And Mike Hagen is a theory collaborator who works with me on all of these projects. Guillaume Duclos, Seth Freden, and Zvonimir Dojic are the people with the experiments and all of the data and cool movies that I showed you today. That's it. I will stop here and switch back to Zoom and see if you want to spend 5 minutes asking me any questions.
Thanks a lot, Aparna. That was a lot of great stuff, a lot of new stuff, but I see some parallels with hardcore materials and dislocation dynamics that I may ask some questions if I can formulate them well. But before I do that, let us open the forum to the audience. Anyone else with questions?
I've switched back to Zoom, so you can type your questions in chat if you prefer.
Yeah.
And I can always share screen and pull up slides and stuff like that if it becomes useful.
So Ankit has a... Oh, Ankit's
just saying I have to go.
Oh, so Aparna, let me start off. I mean, there's a lot to absorb here, right? But is there some parallels you see if you're familiar with the field of dislocation dynamics, especially, the motion of dislocations under shear, the fact that there could be screw dislocations and edge dislocations. I mean, and your plus half the topological defects in terms of looking at positive versus negative dislocations. I mean, is there work being done there, or is there a opportunity the field?
So one way to it's a little, so the analogy that you should bear in mind is imagine I made an active crystal, right? What will happen in an active crystal, if there was such a thing, is that it will spontaneously form dislocations and shear itself.
Yeah.
Right? That is the analog of what's happening here in the active pneumatic. And what people have tried to do, this is not my work, this is various applied math people and stuff like that, and I don't actually understand all of it, is where they've tried to make, so you can define an effective viscosity for the system and things like that, right? And that effective viscosity will be renormalized by the presence of these defects and distillations and stuff like that. So people have tried to make a mapping where you try to define an effective viscosity of the fluid and use the defect density to try to tell you how that viscosity is changed and stuff like that. So there's some effort in that direction, but that's pretty much where it stands right now. And there is some stories associated with braiding and other knot theory type dynamics that may be relevant for the system and things like that. But none of that has risen up to give me some materials level or statistical control over the system that I don't already have. Yes, so I'm responding to a question in the chat, Krishna. The question is, how is all of this related to Turing's pattern formation instabilities, right? So let's think about Turing's pattern formation instabilities for a moment. Forget about morphogenesis and stuff like that and just look at it as a math problem. As a math problem, the Turing thing is a reaction diffusion system, right? You have a reaction and you have a diffusion. And so there's a local activation, long range inhibition, and that gives rise to pattern formation. This can be mapped onto this Turing-like picture for pattern formation and stuff like that, because this is kind of like reaction diffusion in this, but not quite, in the sense that, let's see, it's mechanical reaction diffusion in the sense that the reaction part that appears in Turing is here associated with the nematic melting, right? That happens locally. Rods can all be pointing in one direction or they can randomize locally. So that is the phenomenon that happens locally. And the long range inhibition that one is talking about is elasticity associated with the fact that if you are ordered, then there is a cost to distorting the field far away. So there can be a formal mapping. You can think of this as mechanical reaction diffusion in some sense, in the sense that the reaction and the diffusion are all mechanics of the material. So there's a mathematical mapping in some sense. This is a half-assed idea. There are a couple of papers where people have talked about this a little bit, but it remains to be explored more. Does that make sense? Other questions or comments?
So I mean, I assume, I mean, it's probably pretty obvious, but you can pretty much look at most self-assembly problems using this formulation, right?
Yeah. So inside my head, that doesn't sound right for the following reason. I think of self-assembly as gradient descent dynamics.
Okay.
Right? I mean, there is the nucleation and growth paradigm where kinetics become important and stuff like that. But I think of it as gradient descent. At the end of the day, it looks like gradient descent inside my head. And this is exactly the opposite of gradient descent. This is not going down any free energy landscape. It is does something that is completely non-integrable in its characteristics. So in that sense, it sounds very different inside my head. But I think that there is a connection to self-assembly and stuff like that when you think about self-assembly in a non-equilibrium context, in the sense that your kinetics and things like that are driven. They're not doing some Arrhenius activation to find the states and stuff like that. In that context, I think it is quite closely related to stuff that people think about in self-assembly.
Okay, yeah, I'm just trying to think because we've been working. Oh, Piers has a question.
Can I ask another question? I mean, it's so I'm trying to, so in biological waves, in wave physics, I mean, we can relate classical waves to quantum phenomena, and often we can show that there is the property of some classical waves of classical entanglement, which simply says that those waves are not expressible as a tensor product of subsystem waves. So your system looks very much like that as well to me, that you have this collective behavior that cannot be really separated into subsystem behavior, and therefore are representative of what we call classical entanglements. So can you comment on that?
Yes, absolutely. So you are bang on with respect to that. So let me try to phrase this in the language how I'm understanding what you're saying, and then I'll tell you a little bit, because there's some exciting work that people are doing on this topic. So the way that this works is that, let's imagine that I have my defect as my object, right? And my defects are entangled with each other because of the fact that the nematic elasticity connects the defects even if they are far away. The grad square operator in my thing basically connects the defects from far away. So that's the sense in which they are entangled. And you can't separate them into two defect profiles and take linear superposition of those fields to get the net field. So that's the context of entanglement. And there's this proposal by Jon Dunkel and company. These are people at MIT that claim that this entanglement, this is really a representation of classical entanglement in the language that you proposed, Pierre, and that you should be able to use these kinds of systems to do qubit calculations. You imagine that this is your qubit and it's entangled with that qubit and you make a measurement here and that kind of thing. So there are some proposals where people have played games with this. I'm not super familiar with the literature, but there are 4 or 5 papers where people have explored this idea. So people are thinking along those lines.
But your entanglement or the entanglement or the interactions in some ways or correlations between those defects would be local though. Or are they non-local in the in quantum mechanics? Entanglement is typically non-local, and people talk about those photons you can take to very large distances and they talk to each other and so on. So in your case, are those defects correlated locally or non-locally?
Okay, so if you take the math seriously, like forget about the physical system and stuff like that, and take the math very seriously, then they are entangled irrespective of how far away you take them away, because they're coupled elastically, right? There's an elastic medium in between with a grad square operator. So they're coupled elastically, so they're always entangled however far away you take them. And if you take the theories literally, speed of sound is infinity. So instantaneous elastic information gets propagated across the system. So they are entangled non-locally and will instantaneously talk to each other if you collapse somebody on this side. So math, if you take the math seriously, I don't think any of these assumptions are literally true in the experimental system because, speed of sound is not infinity and there is some screening of the elastic interactions that will happen and stuff like that. But the math is exactly along the lines that you're describing.
Okay, thank you, Aparna.
So Pierre,
right.
are you getting ready for your Nobel Prize?
Yeah, definitely. Next stop. Yeah. All right. Okay,
Good,
thank you.
no, let's see if others have any questions.
Sure.
No, didn't want to, sorry. There are a couple of more minutes. Anyone?
It might be too far out of left field. So.
No, this was great. I think there's, and I think what we've been is woefully under in terms of having such theory-driven talks and bio-related talks. Most of our talks have been, mostly like processing of materials, and it's a very materials engineering course. So this is great. I think hopefully lots of people are still online, which is a reasonably good thing.
Okay, I didn't drive all of them away, so that's a good sign. But they might be watching YouTube on a different window. One never knows.
Hey, that I can't. Yeah,
Pierre. I can ask another question.
Yeah.
I mean, I find your work very, very interesting, Aparna. So it's and it relates very much to some of the work that I do. But I was going to bring your work in the context of topological matter. So you mentioned at the beginning this notion of Ising models and these Ising models or magnetic type models of matter have led to some work on topological matter and so on. So you also mentioned the defects as topological defects and so on. I know that nematic system have been described also through these topological defects and so on. But can you say a few words about the relationship that you see between topological matter and your work, especially in the sense of you also mentioned symmetry breaking at some point. I'm interested in the symmetry breaking in materials and how your interaction or interacting microtubules and so on can lead to symmetry breaking and therefore unusual properties like non-reciprocity in some phenomena.
Okay, so let's take that in a few different pieces of what it is that you're saying. Can I interpret the topological matter statement that you're making to be along, I'm thinking berry face and topological
that's the type of things that I'm talking about.
So
Yes.
let's think about it in that context for a moment.
Yes.
So what people have done is, so what I have here is I have a vector field,
Mhm.
right? I have a vector field. Now, supposing I put this vector field on some non-trivial geometry. That is, I put my vector field on a sphere, or I put my vector field on a catenoid or something like that.
Mhm.
Then there are constraints, right? Associated with putting a vector field on a closed surface or putting a vector field on a catenoid, there'll be constraints associated with putting it there. You can't just put a vector field on that. It's not a Cartesian surface. Then what happens is that exact analogies to ideas like the berry face, write down a berry face and find a gap in your spectrum for fluctuations, and thereby find topological protection around some particular state. So these kinds of things can happen in these theories. So you just take this theory, but to change it from flat space into some screw thing. So that's one context. Another context in which this topological protection and things like that emerge is when you do one of two things. One is you confine these things in, let's say, little wells or something like that, and then couple the wells. So put diffusive coupling between the wells in some way. Then you it's like coupled nonlinear oscillators or something like that, right? So again, you can get a zoo of phenomena that actually looks like the spectrum of a topological insulator or something like that. So that kind of phenomena can come. But wait, what was the other thing that I was thinking? There was one more thing when I was trying to piece apart what you were saying. Now I've forgotten what it was.
Yeah, I cannot read your mind though.
Yeah, I was thinking.
No, but that describes most of the things that I was thinking about as
I
well.
remember. The other thing that where this topological business becomes super important, the topological business, I mean, in the language of hard condensed matter physics, right? When one is trying to look at band spectra and stuff like that, that kind of context becomes important when there are torques. So one of the things I didn't talk about at all today is that if you write down microscopic models that are generating forces, they are different from microscopic models that are generating torques. The considerations are different if your microscopic model is generating torques, because even the symmetry of your stress tensor goes out of the window, and there will be all kinds of crazy continuum mechanics that will show up there. And those kinds of crazy continuum mechanics give rise to equations that can map on to various topological insulator type spectra. So this is something that people think about. It's again not my area of expertise, but the Vincenzo Vitelli at Chicago and a number of other people like that have done some very nice work associated with it. Mark Boeck at Santa Barbara and stuff like that. They've done some very nice work. It's very elegant. Math is very nice.
Okay. No, your system, and what I'm trying to think about is how the work you're doing as a physicist can translate into new approaches or new understanding in material science in engineering, and helping the materials community to understand those concepts. And I think materials systems are also very rich and may show some of these phenomena that you're describing, but we are not aware of them because we don't have the culture nor the knowledge to look at these materials in this specific way. So,
absolutely.
So thanks, Aparna.
Yeah, in my simple mind, I was always trying to map it back to dislocation dynamics. I think there are some overlaps.
No, I think there are some clever analogies that can be made, and actually this is like the crystal melting itself, right? It's not like you're heating the crystal. It's generating forces, generating disclinations, and generating dislocations and melting itself. That's the kind of thing that's happening here. And there are some cool analogies to that. People have actually made some mappings from the kind of story that I was telling you to Kosterlitz-Thouless type transitions, defect mediated melting and things like that. There are some mapping. These mappings are soft in the sense that you have to kind of blur your eyes and not worry too much for the mapping to hold, but they are pretty.
Yeah, any other questions? Oh, Christina was online. I didn't even notice. Okay. No, Aparna, this was great. I think there are, my very slow processing brain, there are some questions, but I need to think through it to articulate it.
Absolutely. Better. You ask me later. We are going to talk anyway.
Yeah. So
liberate everybody else. It's 3 o'clock.
It's actually just 12 here. So they have 3 more hours. No, I think this is great, Aparna. Let me stop the recording and